Our speaker today is Marie Kramer, and she will be talking about graph embeddings and torus obstructions. Welcome, Marie. The floor is yours.
All right, thank you. Thanks for inviting me, and thank you all for coming. So yeah, my name is Marie. I'm a grad student at Syracuse. My advisor is Kennard, and thanks to his NSF grant, I was able to actually come here in person. So I'll be talking about graph embeddings and torus obstructions. So first, so we're on the same page about what we mean by an embedding. So an embedding of a graph G into some surface sigma is a function from G to the surface such that the edges only intersect at images of vertices. Let's look at an example here. So we want to embed K4 into the plane. Here on your left, that's actually an embedding, right? None of the edges are crossing anywhere else besides vertices. Whereas the thing on the right, we clearly have these edges crossing here. So we refer to the thing on the left as an embedding, but the one on the right is not an embedding. By the way, I was saying an embedding, we're embedding things into surfaces. When I talk about the plane, that's the same as talking about embedding onto the two-sphere, but usually we talk about planar things. Now, what if we want to embed K4 into different surfaces? Well, since K4 embeds into the plane, we can just take an embedding of K4 into the plane and put it on some portion of our surface. So here I've done that for the torus and the real projective plane, where I've drawn the torus in the way where we identify this with this, and then also this side with this side. That gives us the torus. And here the normal identifications for the real projective plane where we need to reverse orientations on both of these edges. However, if we now look at, for example, on this picture, if we now look at the faces of the embedding. So by face of an embedding, I mean, basically look at a cycle in our embedding. So a cycle in the graph where there's no vertices on the inside of our cycle, right? So these edges bound the face, for example, but so do these edges here on the outside. They bound this outer face. But if we compare, say, this face here to the outer face here, this face is very nice because it just bounds basically the blue, but it bounds an open disk. So again, it's like a nice planar type thing on the inside here. Whereas this outer face, it's basically where, think about removing a disk from RP2, which gives us a Mobius strip. So this outer face has kind of weird topology on it, which isn't forbidden, but we don't really like dealing with that. So there's actually other embeddings of K4 into these surfaces. So for example, into the torus, we could, right, this edge here connects down here now, and this edge here connects here. So this would be an embedding of another embedding of K4 into the torus. And now, if you spend some time and like piecing together this thing on the outside, it actually turns out that that will also just be a nice open disk. And actually, the same looking embedding also works for the projective plane. Our faces work a little bit differently here, but the idea is the same, that if you piece it together, it will give you nice faces. Okay, what about embedding other graphs into the plane? This is probably one of the most famous examples. I'm expecting everyone in this room has seen this before. I mean, we all know that K33 doesn't embed into the plane. There are multiple different arguments you can give for that. It's been known for about 100 years. One argument I really like is, well, let's just start drawing it. So we take like some long cycle in K33. So we have like the 6 cycle has all the vertices and want to connect each kind of vertice. Like these are green vertices and these are black vertices. And we need to connect each green to each black vertex. So let's just start doing that. Actually, so in this picture here, we have two faces so far. We have this face, which kind of looks like the interior face and an exterior face. But on the plane, there isn't really an interior exterior because we can think about it as a sphere. So it doesn't matter if we put this edge through this inner face or from the outer face, it doesn't matter. And then we keep going. We get another edge, and now we see that we've basically trapped this vertex here, or equivalently this vertex here. We can't connect these two without crossing over an already existing edge. So we try, this doesn't work. Try a different way, this doesn't work. And well, we all know that this is hopeless. Okay, well, if we can't embed into the plane, maybe let's try the real projective plane. Here I've drawn the real projective plane slightly differently. So this is our circle where we're identifying on the boundary x with negative x. And well, let's try it on this surface. Now, this face is different from this face, right? This here will be just, again, something homeomorphic to the plane, whereas this outer face, again, will be more looking like a Mobius strip. Now I'm just choosing, because I want to get a nice picture, that's why I'm choosing to put this edge wrapping around instead of drawing it through the middle here. And now we see, well, if we do this for the other remaining edges, then this edge will come out exactly here, and this edge will come out on the opposite side here. And so we do get an embedding of K33 into the plane, into the real projective plane, not the plane. The real projective plane. Okay, what we saw happening with K33 in the plane was actually that K33 is an obstruction for the plane. So for the purpose of this talk, I'm defining an obstruction for a surface to be a graph G that doesn't embed into the surface, but a proper subgraph. There are multiple different notions of obstructions out there. Oftentimes, we are requiring minors to embed. For the purpose of this talk, I'm talking about what sometimes also referred to as topological obstructions with respect to subgraphs. And that's exactly what we saw happening with K33, right? We saw we could embed the whole graph except for one edge. And since K33 is edge transitive, like no matter which edge we take out of K33, we can embed it. And then famously, Kuratowski showed in 1930 that the obstructions for the plane or equivalent to a sphere are exactly K5 and K33.
Subgraph keeps all the vertices but drops some of the edges.
Yes, you could also remove vertices, including all the incident edges. Okay, then people have studied how can we embed obstructions of the plane into other surfaces. And for example, Mohar showed in 1993, that actually the embedding of K33 that we just constructed into real projective plane is the only embedding. Now, anytime there's something unique in that, there's like up to some notion of equivalence. And that is also the case here, right? Maybe you were like, oh, what if I put this vertex instead of right here? What if I put it slightly below this? So the way we're defining equivalent embeddings is, say you have one embedding and then you have another embedding and they're equivalent if there's some homeomorphism of the surface that maps the image of one embedding to the image of the other, or the image of the graph under that embedding to the other image. And so it turns out for K33 in the real projective plane, no matter how you draw it, there's always going to be a homeomorphism of RP2. If you apply that, you can get it to look like this. So in particular, it also takes care of what if I move my vertices around a little bit, what if I draw my edges a little more squiggly. Then in 2003, Gagarin, Kocay, and Neilson showed that there's two non-equivalent embeddings of K33 into the torus. Here are the two embeddings. This is a different way of drawing the torus. It's, at least to me, every time I look at this, it's not immediately clear to me that this is indeed the torus. But we can start cutting up this picture of the torus and gluing it back together to get the nice square picture. The reason I'm using this one is, well, then the embedding looks nicer. And unfortunately, this embedding doesn't look that nice on this version of the torus. Right, so in this version of the torus, we're identifying these edges in the same orientation, these and these. And here, these two embeddings in particular are non-equivalent. One nice way to distinguish if embeddings are equivalent is to look at what are the boundaries of our facial cycles. So how long are they? Because if, in particular, under any homeomorphism of our surface, it needs to map boundary cycles to boundary cycles of our embedding. For example, here we see we have this 4 cycles that bounce a face. If we look over here, we need to look maybe a little bit harder, but we see in the end that all of the facial cycles have length 6. This one on the inside is clear to see. Then the other ones, it actually, this face, this, and this, that's all one face if we glue them together. And all of these then also have a boundary cycle of length 6. So in particular, these are non-equivalent. Of course, there's more work that goes into showing that these are the only 2 non-equivalent embeddings. Okay, but the sphere isn't the only surface. So what about obstructions for other surfaces? In the 70s and 80s, there was a series of papers by Glover, Huneke, Wang, and Artviken that showed that the complete set of obstructions for the projective plane has 103 graphs. And I believe 35 of those are like minor order obstructions. But since here we're talking about obstruction with respect to subgraphs, there's 106. Here I've listed the 6 cubic projective plane obstructions. Right, by a cubic graph, we just mean a graph for all vertices at B3. And in particular, one of these obstructions is disconnected, which when I first started learning about all of this, I wasn't aware that now we need to consider disconnected graphs, but well, once we start moving away from the plane, we do need to look at disconnected graphs.
These are the only cubic ones?
Yes, these are the only cubic ones for the real projective plane.
Okay. There's just one that's not taken in this list. Just the disconnected ones. The others are all.
Yeah, that's one here. Yeah, that's in this 2.
So then there's 1, 2, 3, 4.
Yeah. Okay, let's think about obstructions for other surfaces. Thanks to Robertson and Seymour's minor project, where they published a lot of papers, we know that every surface has a finite list of obstructions, but we don't really know how to find these obstructions for any given surface. And they're also, I'm not sure how much is known like asymptotically, how much we expect. But at least we know it's a finite list for every surface. But that's about where the good news of this ends. So for the torus, there are at least 206 cubic obstructions, and it is believed that that list is complete. Part of this was done by Chambers in his master's thesis, using computer algorithms, exhaustive searches, And part of this conjecture, these are based on they started looking at larger and larger graphs, and eventually they found no more obstructions. And if you kind of look at the data of their obstructions, it seems believable that they found them all, but there's no proof as of yet that there's actually exactly 206 cubic obstructions. If we drop the word cubic and just look at torus obstructions, there's over 250,000. To this day, there's like a list online where people contribute to, oh, I found a new torus obstruction. A lot of the work is computational, and part of what I'm interested in is learning more about what does the structure of these obstructions look like. There is even less known about the Klein model. There is a classification of Klein model obstructions of connectivity 2. I believe there's something between 600 and 700 of those, but that's one of the only results that is known so far.
Just a quick question.
Yes.
Is there a reason why we care about the cubic ones specifically? Like, I can sort of buy it.
Yeah, that's a great question. So looking at the history of how people found the projective plane obstruction, actually before Glover, Nick, and Wang published their paper in '79 about all the projective plane obstructions, they first also looked at the cubic ones because they're just a really nice class of graphs to work with. It just gives a nice restriction. Yeah. In a second, I'll talk about why or more specifically, my advisor cares about cubic graphs, which comes from a completely different direction. But yeah, part of looking at cubic graphs is really, it gives an first idea of which techniques to use, and it just makes it more manageable. Okay, let me talk about why my advisor cares about this. So everything that I'm talking about, I mean, I find that fascinating just from a graph theory point of view. I come very much from a graph theory background. My advisor is a Riemannian geometer. But together with his collaborators, he found an application of graph embeddings to geometry that actually helped them solve one of their problems. And as it turns out, if we know what an embedding of a graph or a weighted graph into a surface looks like, we get bounds on the weighted girth or systole of a graph. So let me illustrate a little bit of what I mean by this. We take our embedding of K33 into the real projective plane. In particular, this gives us 4 faces. All of these are bounded by some facial cycles. And now if we imagine that we have some weight function on the edges, so all the edges have some non-negative integer. And these CIs are the facial cycles around each face. So if we sum over those weights and all the facial cycles, then, well, we will have counted each edge twice, because each edge is part of 2 facial cycles here. So if we sum up all of these weights of the facial cycles, we get twice the total weight of our graph, which in particular means that there has to exist some facial cycle whose weight is at most half of the total weight, right? Otherwise, if all of these are really large weight, we would never get that in the sum. This is twice the weight. So we get an inequality like this, which then in particular bounds the systole, right? The systole is just like the weighted girth and perhaps normalized by the complete weight of the graph. So for some weight function, we get that the systole is at most 1/2. This isn't the optimal bound for the systole, but it gives like an idea of why we care about graph. There's also a formula that they discovered about relating the systole to what kind of surface the graph embeds into. So their formula depends on the Euler characteristic of the surface and the Betti number of the graph. So the Betti number of a graph is the same as the cyclomatic number, or yeah. So how many edges do we need to remove?
And what's a cyclomatic?
How many edges we need to remove to no longer have any cycles, so to turn it into a tree or a forest. And part of the system bounds is also why, for my problems, I care about cubic graphs, because it turns out that the system, like the cubic graphs, are the worst cases for these system estimates. So some of cubic graphs have the largest system. And then by the summatroid theory, the system bounds give some geometric bounds on the fixed point set data for some torus representations, which is what my advisor was working on, which then in turn translates to having applications to classifying Riemannian manifolds with positive curvature and torus symmetry. But even if you don't care about this geometry application, the rest of the talk is still interesting, I think. And this is kind of why my advisor got interested in it, and in the end, why I'm currently working on these problems. Okay, so one thing I looked at was if I take a cubic projective plane obstruction and I want to embed it into the torus, and how many different ways is that possible? All right, so similar to when people studied how many ways can K33 embed into RP2. And what we found is that the graphs are, these graphs are H0 through H5, labeled from left to right. The graph H0 does not embed into the torus. The graph H2, which is this one, embeds into the torus in exactly 4 ways. And each of the remaining 4 graphs embed in the torus in exactly 2 ways. Again, all of this up to that notion of equivalence of homeomorphisms of the surface. Okay, now I want to give you a little bit of an idea of how we go about proving this. So the graph H0 does not embed into the torus is a nice warm-up example. This is also, people already knew that H0 doesn't embed into the torus. But let's just take a quick look at this. So H0 is this graph. It's just a disjoint union of 2 K33s. And luckily, we know exactly how K33 embeds into the torus. There's these 2 ways. And if we analyze these embeddings a little bit, we'll notice that each of these faces is homeomorphic to an open disk. So basically, each of these faces behaves like the plane. I mean, it's clear for these 2, and then this on the outside, that's all one face. If we sit down for like probably 2 minutes and glue these together in the right way, we'll see that that indeed is also a disk, and same for the embedding on the right. But now we see our problem. All right, this is the first copy of K33 has to look either like this or like this in the torus. But now we want to embed the second copy of K33, but since we can't cross over any of the already existing edges, we are now stuck because now it looks like we have to embed K33 into something that looks like the plane, which we know is impossible. Also, embeddings where each face looks like the plane are called cellular embeddings. But yes, we see that H0 really does not embed into the torus. Okay, that was nice and easy. Would be great if the other stuff was as nice and easy, but now I know how it goes. So I'll give a short overview of how we determined that H1 embeds in exactly 2 ways into the torus, and then the remaining graphs we used similar ideas. So these are the 2 embeddings of H1 into the torus. They look very, very similar. The only difference is that this portion here looks like it's just flipped. But everything else looks the same. Okay, so first, this is our graph H1. we know that H1 doesn't embed into the real projective plane, and we know that it's cubic. Well, if it doesn't embed into RP2, then it can't embed into the plane either, so, and it's cubic, so there has to be a K33 in there. You have multiple options of choosing your K33, right? What I mean by K33, and there is a subgraph that's homeomorphic to K33. So for example, this edge here has a bunch of degree 2 vertices on it, so we just subdivided one of the edges. You could choose a different K33 in here. It would still work. We just decided to choose one where all the vertices are somehow present in that subdivision because that gave us more to work with. So we're choosing this version of, or we're choosing this K33 subgraph. And then we needed to know something about certain types of embeddings of K33 into the torus, something that we end up calling edged embeddings. And by that, we mean that it's an embedding of K33 into the torus where there's like one special highlighted edge. And we needed to know where one of the edges was in our embedding, because then this would be the subdivided edge where we would then need to add some edges between those degree 2 vertices to build H1 out of K33. So for example, if we have an embedding where we highlight this edge, that would be equivalent to an embedding where we highlight this edge. Just think about rotating this picture, which would translate to a homomorphism of the torus. Or similar here, highlighting this edge, we again think about rotating and reflecting potentially. Turns out to be the same as highlighting this edge. And it actually turns out that for this embedding of K33 into the torus, all of the edges play the same role in this embedding, which it took us a little bit to see that these edges that kind of, I always call them wrapping around, that these edges actually play the same role as these edges. That takes a little bit of investigation. Yeah.
So all the KTVs that you can find in H1 just have a single subdivided edge, which is why you only care about one.
No, so we could also. Oh, sorry, I think I misunderstood your question.
It looks like you're just taking one edge and you're just subdividing it.
Yeah. Yeah, so the thing is, you could do, even if you chose a completely different looking K33, you could still basically use a similar technique. You would potentially just, so for example, instead of having the subdivided edge involve all of the vertices, we could take a shortcut here from 3 to 6. That would also be a K33 subgraph, but then we just have less information about how the vertices of H1 look like in our embedding, because then we have these two floating vertices which have to go somewhere. So the idea here is that we choose one K33 that makes our life easy. In the end, if you chose a different one, you could go through similar arguments, you'd arrive at the same conclusion. Actually, at first, I think I did it one way and my advisor did it another way. And we got to the same conclusion. Then we just went like, okay, we take the easiest K33 that gives us the most information. So you have some choice here, but we just make the choice that looks nicest to us. All right, so once we know that we have these 5 edged embeddings, now all we need to do is add 3 edges to it to build our K33. So we have these 6 vertices, and let's actually zoom in on that picture for a second. We have these 6 vertices here, and we need to connect like this vertex to the one that's distance 3 away. This vertex to the one that's distance 3 away, and same for this one. And if we start doing that, both of these here are just looking like an open disk. And if we start doing that, we'll soon realize that we're going to trap ourselves. Right? If we connect this one around this way, then these two vertices can no longer have edges coming out in this direction because they're trapped. And then we connect this one around this way, but now the last vertex is completely trapped and cannot connect here. And very similar, so in particular, this embedding of K33 doesn't extend to an embedding of H1. And very similar arguments work for all of the embeddings except for the second one. Because what all of the embeddings except for this one have in common is that our highlighted edge borders two faces, two distinct faces that both look like an open disk. Whereas in the second case, this edge touches the same face twice. So that means we're more looking at something like a cylinder, where we now have more flexibility to add our edges, particularly we no longer trap ourselves in. And so the second edged embedding actually extends to an embedding of H1. And at first we get 4 pictures, but we said there's exactly 2 ways. So we better get that some of these pictures are equivalent to each other. Some of these embeddings are equivalent to each other. And it turns out that yes, they're pairwise equivalent. So the one that was on the very left, the one was on the very right, they're equivalent, and they're equivalent to this nicer John embedding of H1 to the torus. Instead of writing down like what the homeomorphism of the surface is, I first tried to do that. It was a nightmare. So then I started thinking about how embeddings of graphs into surfaces can also be described combinatorially using rotation systems. I won't go into rotation systems in too much detail, but if any of you is familiar with those, that's where this idea basically comes from. So what we started doing is, okay, let's basically cut up our torus according to the faces that we have. So we cut it up into different polygons. And then when we want to use these polygons to then build the torus back, we have to like identify the edge 1, 2 that shows up in this square here with the edge 1, 2 showing up in this larger face. And that's how we can use polygons to describe an embedding of a graph into a surface. And then we could label, there's some trial and error going in here because maybe the first way we label it doesn't quite work out, but we can label these embeddings in a way that we have the same polygons that we glue together in the same way to build the torus, and same in this embedding. And then we can do a similar thing for embeddings 2 and 3, but in particular, we can't find a way to label embedding 1 and embedding 2 in the same way. So if we get the same gluing map. So 1 and 2 are not equivalent, but 1 and 4 are, and so are 2 and 3. All right, and that's the idea of how we show that H1 has exactly 2 ways to embed into the torus, and then very similar ideas work for the remaining cubic projective plane abstractions. We just need different versions of this lemma because sometimes we need more information about how K33 is embedded into the torus exactly. If you're interested in this, there is a preprint on arXiv with exactly these results. Now, maybe it seems kind of arbitrary. Why are we looking at how do projective plane abstractions embed into the torus? And the motivation for this actually comes from trying to find torus obstructions. And by find torus obstructions, I more mean find a theoretical way to describe torus obstructions and learn more about their structure. Because computationally, these torus obstructions were already there, but I wanted to learn more about why do they look this way. Maybe that will help us in the future to figure out that there are exactly 206 cubic torus obstructions. So here I'm looking at cubic graphs of Betti number at most 8. So essentially this just means that we don't have too many vertices in our graphs. For the geometry application I was mentioning earlier, we would like to have the graphs be a little bit bigger. I haven't gotten that to work yet. But for now, we're looking at relatively small cubic graphs. And if G is such a small cubic graph and it doesn't embed into the torus, then G is one of 11 graphs. Here, I've only drawn 10 graphs. And there's this weird notation G1 union an edge. What I mean by that is we take our graph G0, which is the graph where we see the disjoint union of K33s, and we subdivide one edge in each component. So we subdivide one edge up here, one edge down here. Doesn't matter which edge, because K33 is edge transitive. We subdivide them, we add an edge between the two new vertices. In particular, this will connect our graph. Okay, let's take a look at why this is true. So we split up the proof into 2 cases, and it's sorted by either the graph G it doesn't embed into RP2 or it embeds into RP2, which at least to me seems kind of arbitrary at first. Why are we caring about embedding it into RP2 if we're trying to embed it into the torus? But it just turns out that all of these 11 graphs, none of them embed into RP2. So that seemed like a good strategy. And then we just hoped that it would work out. Okay, if our graph G doesn't embed into RP2, then it has to contain one of these 6 cubic projective plane obstructions that we discussed. And then we go through what if it contains H0, which was the disconnected, the 2 copies of K33, and the Betti number of H0 is 8. So in particular, that is the largest Betti number that we want for our graph G. So if G contains H0, then, well, one option is that G is just H0. And actually, as it turns out, yes, G0 is also this disjoint union of 2 K33s. And we already saw that the disjoint union of K33s does not embed into the torus. But then if you remove any edge from that, then you get the disjoint union of K33 with K33 minus an edge. And then the problem that we had about trying to embed the second copy of K33 into the plane no longer exists, because then you try to embed K33 without an edge into the plane, which we know works. So it itself doesn't embed, but any subgraph does. And then, well, if we add an edge to it, that's not going to make it embeddable into torus all of a sudden. One note about this, usually adding edges will increase the Betti number by 1. However, if we add an edge to a disconnected graph in a way that connects it, then it doesn't increase the Betti number. Now, what if G contains H1? H1 has Betti number 7, and we know that H1 itself embeds into the torus in 2 ways by the theorem we just saw. So H1 itself isn't going to be on this list, but then we decided let's build graphs from H1 that have Betti number 8. So let's see how we can do that. So again, we subdivide two edges in H1 and add a new edge between the 2°2 vertices. So that preserves cubicness, everything is nice. The problem is that many of these graphs that we build in this way are going to be isomorphic. So for example, this graph and this graph, so the black graph is our graph H1, and then the red edge and the red vertices are the newly added things. These two graphs are isomorphic, right? You can just think about this, switching things around here and down here to see that relatively quickly. And we don't want to be stack listing a bunch of isomorphic graphs and then deal with all of those. So what we did is we looked at edge orbits. And so, okay, which edges can be swapped in our graph? And then what we found from that is that there's basically only 3 kinds of edges in this graph. There's like these edges in this 4th cycle here, these 2 edges that make a 2-cut in this graph, and then these remaining edges. And that just helps us not list the same graphs over and over again. So for example, if we start attaching new edges to this, then we say, okay, our first new vertex is on one of these red edges. But then we just pick one and say, without loss of generality, let it be this one. And then we go from there. So that just helps us not list a ton of graphs a ton of times. What we found using these edge orbits and some other observations about these graphs is that there are at most 9 pairwise non-isomorphic graphs we can build in this way. We didn't go through and carefully check that they're really all non-isomorphic. Once we get it down to 9, we're like, okay, we can do this now. So there's at most 9 of these. And after some analysis, we found that actually 4 of these graphs are showing up on our list. And well, we are currently building that list, so we need to give an argument as to, okay, if like G1 is one of these graphs that we built by attaching an edge to H1, why does that not embed into the torus? Well, we took our 2 embeddings that we know H1 has into the torus and just check, can we attach the missing edge to build our graph G1, for example. And there is some more case analysis to be done here, because now we kind of need to look at labeled embeddings of H1 into the torus, because attaching an edge to build G1 depends on where exactly are we attaching this edge. So there is some case analysis to be done here, but this is how we can show that these 4 graphs, 4 of these 9 graphs don't embed into the torus, and then for the remaining ones, we just give them embedding to the torus. Then the idea if G contains H2, H3, or H4 is exactly the same. They also have Betti number 7. We attach an edge to it to make it Betti number 8. And as it turns out, all of these graphs will embed into the torus. So the last case, if G contains H5, again, it is similar, but it was just more annoying because H5 is smaller. It only has Betti number 6. So to get it all the way up to Betti number 8, potentially, we're going to have to attach 2 edges. So attaching one edge in the way we've been doing increases the Betti number by 1, unless you have a disconnected graph. So we have to analyze graphs of the form H5 union an edge and then another edge, where in particular this second edge could attach to the edge that we added in the first step. And well, if H5 has how many edges? 13 edges? No, 15 edges. So if we just start attaching edges to all of these edges, we're going to get something like 15 to the 4 graphs. We just like very mindlessly start attaching them. But again, we're going to use some edge automorphisms of H5 and some other things about 4 cycles in these graphs to get it down to approximately looking at 75 graphs. And we didn't go through it 100% carefully, so there's still isomorphisms between these 75 graphs potentially, but that's not a lot more manageable than I don't even know how many graphs there would be if we just attach these 2 edges. But luckily they split into nice families, and we can do it like family by family, and then at any given time we're just looking at 20 graphs or so. So it's not too overwhelming in the end. And what we then find using this is that G4 through G9 don't embed into the torus, and G4 shows up twice. And it turns out that G4 contains both H1 and H5. Okay, that was the first case. We already found all of our graphs that we wanted to find. So now we need to argue why we don't get any more graphs if G does embed into RP2. This is actually a pretty quick and nice argument. Well, we do need to do some work. We need to establish that if we have a cubic graph with Betti number at most 8, then there exists an embedding into RP2 of face width at most 3. I'm not going to go into too much detail about what the face width of an embedding into RP2 is, but we're going to be into this pictures like this. So this is the majority of the graph is happening here. And then there's just 3 edges that kind of, I always say, see the topology of RP2. So for these 3 edges, we need to make them go round. The more formal definition involves intersections of edges with an essential cycle in RP2, but this is kind of the picture we're going to be working with. And now there is a more general result by Wiemeler, Hunicke, Richter, and Robertson that projective embeddings of a certain face width imply the existence of an embedding into an orientable surface of a certain genus. In particular, this gives us, if the face width is at most 3, we get an embedding into the torus. But actually, we can also very quickly see this from our picture. Right, if we want to, instead of having this graph on RP2, we want to have it on the torus. We still have our majority blob of the graph in the middle here. And then we can still have, say, this edge going around here. One of the other edges can also just nicely just use this identification. And then we need to make sure that they come into our rest blob in the correct order. So that's why for this last edge, we can't just go out and in, because then it attaches in the wrong order to the rest of our graph G. But if we wrap around all the way like this, it goes there in the right way. But as I said, there is a more general result in this area. But once we have that, we are done. Right, because we have all the graphs we're looking at have such a small face width embedding, so they all embed into the torus. All right, and that brings me to the end of my talk. These are some selected references. Thank you all for coming, and if you have any questions.
So why did you use minor order? Why did you take into consideration minors so that you could talk about minimal obstructions?
Yeah, so it actually, if we're just being in the class of cubic graphs, so if we want cubic graphs and everything should stay cubic, then actually minor order and the topological obstructions are the same. but just if everything is restricted to cubic graphs. But we only realized it afterwards. But once we've done that stuff. We have some ideas for like future work, even if we want to keep restricting to cubic graphs, it might be helpful to go to minors because that sometimes gives some nice insight into things. But part of it also comes from the application to geometry where it's just not natural to talk about minors. It's more natural to think about taking out edges, putting edges back in. But yeah, I think definitely it would be.
You said just taking out the edges and putting edges back in, so just edges, not vertices.
Yes. I mean, the thing is, we kind of ignore. So in a way, we are secretly contracting edges because oftentimes the way we've been thinking about is if we take out an edge or something, then we have degree 2 vertices left, and we think about ignoring these. So secretly, we are contracting edges there to not have the degree 2 vertices anymore, which technically for topological obstructions that is allowed, like you are for topological obstruction, you are allowed to contract an edge just one endpoint of degree 2. But yeah, I think the main reason is from the geometry application. It's more natural to think about it with just subgraphs. But I would be interested in continuing this work and more thinking also about minors, because that's always a big question. Is it also a minor order obstruction? And there's certainly going to be less of those.
So the questions during the talk. Let's thank the speaker. Lunch upstairs. So we'll go to lunch upstairs since we have quite a few of us.